Hi, welcome to another mathematics lesson. My name is Kingsley Linus. In today's lesson, we'll be looking at the topic conversion of base 10 numerals to binary. By the end of this lesson, you should be able to define number bases. You should also be able to convert numbers in base 10 to base 2. And lastly, you should be able to convert numbers in base 2 to base 10. When you come across number base, it is important to find out what a base is. Simply put, a base is like a foundation or a platform upon which we build. Certain things are usually counted in groups. For example, eggs. A crate of eggs has 30 eggs. The days of the week are 7. Time is usually measured or counted in seconds. Number bases are like foundational blocks we use when we count, calculate, or measure things. Now, in this lesson, our focus is on base 2 and base 10. The number base you employ in counting any group of objects determines the number of available blocks you have. For example, the base 10 number system is a unique system of counting where we have 10 unique digits, which are like 10 blocks. Now, these 10 unique digits are the digits 0 to 9. With these digits, we can form other larger numbers. Now, the binary number system or the base 2 number system is a system where we count in groups of 2. This system has just 2 unique blocks, 0 and 1. Now, let's move on in this lesson to find out how we can convert numbers in base 10 to base 2. Converting base 10 numbers to binary is quite easy. Now, how do we do that? One of the methods we employ in converting base 10 numbers to binary or base 2 is expressing a given number as a sum of multiples of the powers of 2. Alternatively, we can use the remainder method. Now, we have an example. We are expected to use the sum of multiples of powers of 2 to convert the number 9 in base 10 to base 2, and we'll convert 62 in base 10 to base 2. Now, let's look at how we go about this. The number 9 in base 10, we must first split it into multiples of powers of 2. And the closest or the biggest multiple of 2 here is 8. And then we have 1 as the remainder. So 8 plus 1 gives us 9. Now, 8 as a multiple of power of 2 is 2 raised to power 3. And 2 raised to power 0 represents 1. So, we can go ahead to express this number in base 2. The first number we have, 2 raised to power 3, will be expressed as 1 multiplied by 2 raised to power 3. Since we don't have 2 raised to power 2, we will sum 0 multiplied by 2 raised to power 2 and 0 multiplied by 2 raised to power 1. And lastly, we have 2 raised to power 0, so we have 1 multiplied by 2 raised to power 0. Now, this number in binary is equivalent to 1001 base 2. So 9 in base 10 is equal to 1001 base 2. Now, to the second example, we can express the number 62 in multiples of 2 as 32, 16, 8, 4, and 2. Now, 32 in base 10 can as well be written as 2 raised to power 5, and 16 as 2 raised to power 4, and 8 as 2 raised to power 3, 4 as 2 raised to power 2, and 2 as 2 raised to power 1. Now, we can go ahead to express them in the base 2 system. So we have 1 multiplied by 2 raised to power 5, 1 multiplied by 2 raised to power 4, 1 multiplied by 2 raised to power 3, 1 multiplied by 2 raised to power 2, 1 multiplied by 2 raised to power 1, and 0 multiplied by 2 raised to power 0. That gives us 1, 1, 1, 1, 1, 0, base 2. So 62 in base 10 is giving us this. Still talking about the conversion of numbers in base 10 to base 2. This table here shows the first 10 significant numbers of the decimal number system and their equivalents in the binary number system, expressed as the sum of multiples of the powers of 2. Do well to go through this table and understand how these conversions were done. I mentioned earlier that the second method of converting decimal numbers to binary is the use of the remainder method. Let's find out how this remainder method works. Whenever we choose the remainder method to convert base 10 numbers to base 2, we must take the following steps. Number 1, divide the given base 10 number repeatedly by 2 and note the remainders. Secondly, we must keep dividing until 0 is obtained. And lastly, write out all the remainders in the reverse order, that is from bottom to top. Now here is an example. We are expected to convert some numbers using the remainder method. The example says convert the following to base 2 numbers. First, we have 623. And then we have 20 whole number 3 over 4. Now 623, we have to arrange it on our table like this. And then we start by dividing the number with 2. 623 divided by 2 gives us 311, remainder 1. 311 divided by 2 gives us 155, remainder 1. 155 divided by 2 gives us 77, remainder 1. 77 divided by 2 gives us 38, remainder 1. 38 divided by 2 gives us 19, remainder 0. 19 divided by 2 gives us 9, remainder 1. 9 divided by 2 gives us 4, remainder 1. 4 divided by 2 gives us 2, remainder 0. And 2 divided by 2 gives us 1, remainder 0. 1 divided by 2 gives us 0, remainder 1. So we take our numbers just in the direction of the arrow you can see, and we list out these numbers in this manner. So we have 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, base 2. So the number 623 in base 10 is equivalent to this. Now moving on to the next example where we have 20 whole number 3 over 4. We are going to take the whole number first, which is 20. And in the same manner, we will keep dividing the number 20 by the number 2 until we have nothing left. Now, 20 divided by 2 gives us 10, remainder 0. 10 divided by 2 gives us 5, remainder 0. And 5 divided by 2 gives us 2, remainder 1. 2 divided by 2 gives us 1, remainder 0. And 1 divided by 2 gives us 0, remainder 1. So we list our numbers in this direction. But before we do that, we have to consider the fractional part. The number 3, if you recall the table in the previous slide, the number 3 in base 10 is equivalent to 1, 1 in base 2. And the number 4 in base 10 is equivalent to 1, 0, 0 in base 2. Now, ordinarily dividing 1, 1 just assume it is 11 in decimal and 100 is 100 in decimal. We can divide that to get 0.11. But don't forget, we are still in base 2, so we have that as base 2. So we can now list the numbers we have for the whole number part and then what we have for the fractional part. So 20 whole number 3/4 in base 10 is equivalent to 10100.11 base 2. I hope that was clear enough, converting decimal numbers to binary. Now, how about binary numbers to decimal? Let's take a look at that. Binary numbers can be converted to decimal by simply expressing our numbers as sum of multiples of powers of 2. That sounds similar to what we have done in the past. Now, doing that is quite easy. We have an example that says convert the following binary numbers to base 10. 1000, 100, Now, to do that, we can go ahead to express these numbers as sums of multiples of powers of 2. And how do we go about that? 1000. So we have 1 multiplied by 2 raised to power 3, 0 multiplied by 2 raised to power 2, 0 multiplied by 2 raised to power 1, 0 multiplied by 2 raised to power 0. Now notice that if we have 4 digits here, like what we have, then our highest power will be 3. The next step is to evaluate the values of each of these. 1 multiplied by 2 raised to power 3. 2 raised to power 3 is 8. 8 multiplied by 1 gives us 8. 2 raised to power 2 is 4. But 4 multiplied by 0 gives us 0. 2 raised to power 1 is 2. But 2 multiplied by 0 gives us 0. And 2 raised to power 0 is 1. 1 multiplied by 0 gives us 0. So our answer is 8 in base 10. So the number 1000 base 2 is equivalent to 8 in base 10. Now, moving on to the second example, we have 100.111 base 2. So just like we had in the first example, we go ahead to express our numbers like this. But notice that from the decimal point, the powers of 2 changed. We have -1, -2, and -3. This is how we express decimal numbers. The next step is to solve through. 2 raised to power 2 is 4. 4 multiplied by 1 gives us 4. 2 raised to power 1 is 2. 2 multiplied by 0 gives us 0. So we don't need to list it. 2 raised to power 0 gives us 1. 1 multiplied by 0 gives us 0. Then 2 raised to power -1 is equivalent to 1/2. So we have 1/2. And 2 raised to power -2 is equivalent to 1/4, as well as 2 raised to power 3 is equivalent to 1/8. So when you solve through this, you have 4 whole number 7/8. Of course, you know, at this point, you find the LCM when summing all of this. And 4 whole number 7/8 is the same thing as 4.875. So the number 100.111 base 2 is equivalent to 4.875 base 10. So I have an exercise for you. Pause this video and try out these questions. I'm sure you are done. The answer to exercise 1 is 1001101 base 2. The answer to exercise 2 is 0.1111 base 2. And lastly, the answer to exercise 3 is 13 whole number 9/16 or 13.563. If these were your answers, you are correct. With this, we have come to the end of this lesson. But before you go, let's look at a summary of all we've learned today. First, we learned that number bases are like the foundation blocks we use daily when we count, measure, or calculate things. We also learned that the number-based system the world uses today is called the decimal number system. Going on, we learned that numbers in the decimal number system can be converted to binary numbers by expressing a given number as a sum of multiples of the powers of 2, or by using the remainder method. And lastly, we learned that numbers in the binary number system can be converted to decimals by expressing the given numbers as sums of multiples of powers of 2 and summing. I'm sure you know it's test time. I have some test questions for you. Question 1. Convert the base 10 number 244 to binary number. The correct answer is option B. Question 2. Convert the binary number 1100111 to base 10. Option A, 201. Option B, 103. Option C, 121. And option D, 240. The correct answer is option B, 103. I'm sure you learned something new in today's lesson. Till I see you again in another lesson. Bye-bye.